Hello, everyone, and welcome to The Fight Against Runoff, a study of hydrology applications. Today's presentation will be about 30 minutes, followed by about 10 minutes of Q&A with our presenter, Leo Rivera, whom I will introduce in just a moment. But before we start, we've got a couple of housekeeping items. First, we want this webinar to be interactive, so we encourage you to submit any and all questions in the questions pane, and we'll be keeping track of these for the Q&A session toward the end. Second, if you want us to go back or repeat something you missed, don't worry. We will be sending around a recording of the webinar via email within the next 3 to 5 business days. All right, with all of that out of the way, let's get started. Today, we'll hear from Leo Rivera, who will break down the multitude of applications for hydraulic connectivity. Leo is a research scientist and director of science outreach at Meter Group. He earned his undergraduate degree and master's in soil science at Texas A&M University, where he helped develop an infiltration system for measuring hydraulic connectivity used by the NRCS in Texas. Leo is the force behind application development in meters hydrology instrumentation, including the SATURO, HYPROP, and WP4C. He also works in R&D to explore new instrumentation for water and nutrient movement in the soil. So without further ado, I'll hand it over to Leo to get us started.
All right. Thanks, Brad. And thank you, everyone, for joining today's webinar. I'm excited to, of course, talk about one of my favorite topics, and that's measuring hydraulic conductivity. That's, of course, where I spent a lot of my time early in my graduate studies and in my career. So it's always fun to talk about those measurements and especially to dive into some of these applications. So the goal of today's webinar is a little different from previous webinars I've given, where we're actually going to more so dive into some different applications that we've seen where people are using hydraulic conductivity data to better understand a different topic. Some of those things might be runoff, where the webinar gets its name, but there are other things, of course, that people are using this measurement to take a look at, and we're going to dive into that today. But before we get into the applications, I always like to start with the basics and define what it is we're even talking about. So what is hydraulic conductivity and why do we care about? Well, one of the reasons we care about hydraulic conductivity is it impacts almost everything soil is used for. It impacts crop production, and especially when you think about our understanding of irrigation and drainage and how to apply irrigation effectively and efficiently. Of course, it really has a big impact in hydrology, whether you're looking at native or urban settings and environments, and we'll dive into some of that in some of these applications. Landfill performance is also a big area where hydraulic conductivity measurements are important, whether our goal is to reduce infiltration of water into soil and into the landfills, or to store water in the landfill cover itself as a part of an ET system, things like that. They all plays a really important role there. And then, of course, when it comes to stormwater system design, and again, going back to our goal of trying to control runoff, especially in urban environments, and especially as we've developed more concrete cities with less impermeable surfaces, stormwater system designs become more and more important. And then lastly, of course, our understanding of soil health and what are the factors that tell us whether a soil is healthy or impaired. Hydraulic conductivity is one of those important factors that helps us understand soil health and how our management practices are impacting soil health. So, of course, what factors determine or impact hydraulic conductivity? So the primary factors that determine what the hydraulic conductivity of a soil is are things like soil texture, soil structure, the biopores that exist or the absence of biopores, and we'll talk about one of those examples in one of the case studies, things like wormholes, things like that. And then, of course, compaction and the density of the soil. So what, how we're impacting the soil through trafficking and things like that. And then, of course, and you'll hear a little bit about this, but I would recommend diving more into this, is water content and potential. The antecedent conditions can actually impact how the water infiltrates, how the soil infiltrates water, especially in expansive soils. That plays a really big role. And of course, it's important to understand how we actually make these measurements. So traditionally, the way these measurements may have been made in the field, we're using things like a double ring infiltrometer. And the way a double ring infiltrometer works is you have a concentric cylinder system. So you have an inner ring and an outer ring. And that outer ring is designed to buffer the flow of water around that inner ring. So that way we're getting primarily one-dimensional flow in that inner ring. And that's an assumption that we've made with this measurement. Now, as you dove into the literature, we know that that assumption is false. And so we still have to make corrections for three-dimensional flow from double ring infiltrometers. But what's really great about a tool like this is we can do constant and falling head techniques for measuring infiltration and hydraulic conductivity in soil. Of course, this is something that I personally have a lot of experience with. This is a picture of a setup that I use in grad school to go out and measure hydraulic conductivity across different landscapes and land uses in Texas, and looking at the impacts that land use and landscape have on soil hydraulic properties. You can see the setup here was quite massive. It had a huge water tank and big rings, and it took a lot to take these measurements. And as you can see, we spent a lot of time in the field waiting for these measurements to be completed. And of course, that led us to work on trying to develop better tools to make these measurements. And so a lot of that experience is what went into developing tools like the dual head method that we use in the SATURO that you can see here, that really simplifies the measurement itself and simplifies the ability of a user to go out and make these measurements and make them accurately. And so this is what we continue to evolve and do and try to make these measurements better so people can go out and use these more broadly in their studies. And so instead of focusing on the measurements themselves like we traditionally have, we're going to focus on some of these applications where these measurements are being used. So we're going to start with this first case study here. And this case study comes from S.I. Applebaum et al. 2022. And this case study is comparing grazing ecosystems. So grazing ecosystems have co-evolved with ruminant grasses and soil biota, contributing to carbon-rich soils over the last 40 million years. This coevolution has contributed to the global expansion of carbon-rich soils in grassland regions, which cover approximately 40% of the global land area. However, modern practices often degrade these ecosystems. In most rangelands, free-ranging wild herbivores have been replaced by fenced-in livestock. We've all seen this. This shift has often led to the degradation of the vegetation and the soils, resulting in declines in productivity, biodiversity, and ecosystem resilience. Because of this challenge, various grazing management strategies have been developed to provide sustainable resource and economic outcomes. These include continuous grazing, which you might see referred to as CG in the text, rotational grazing, which is typically referred to as RG, and adaptive multi-paddock grazing or AMP grazing. And I will primarily just refer to that as AMP grazing because that's a really long phrase to say. But the goal of the study from Applebaum et al. Was to compare the continuous grazing and the AMP grazing in the southeastern U.S. And if you're not familiar with AMP grazing involves short grazing events with planned recovery periods, while continuous grazing, as the name states, means continuous grazing with no planned recovery. The study aims to examine the effects of AMP and continuous grazing management on things like plant species, richness, diversity, dominance, and cover, vegetation stands and crop biomass, water infiltration, soil carbon levels, the amount of bare ground, fine litter cover, and nutrient cycling across these different areas. And their study utilized what they called an across-the-fence comparison framework. And so what that means is the study used paired ranches with similar biophysical conditions, comparing AMP and continuous grazing. And some of their measurements included looking at plant species richness, biomass, water infiltration, like we said, soil carbon, and these data were collected from ranches in Kentucky, Tennessee, Alabama, and Mississippi. The results of their findings showed differences in a few areas, and we're going to show some of that here. When looking at vegetation cover, looking at vegetation cover impacts, AMP grazing increased vegetation cover and diversity, especially in southern sites. And conventional grazing sites had more bare ground and less plant cover, as you would expect due to the reduced or the lack of recovery periods. These grazing impacts also, or these grazing differences also impacted the soil hydraulic properties as well. When we look at water infiltration, you find that the AMP sites generally had higher water infiltration rates and field saturated hydraulic conductivity. As you can see in the table here on the left, you can see comparisons of these paired sites, and you consistently see, you almost consistently see higher hydraulic conductivities in the AMP sites than in the continuous grazing sites in almost all of the pairings. And this is typically an indicator that these AMP sites have better soil health. And then lastly, AMP grazing resulted in higher soil organic carbon stocks, enhancing soil fertility and carbon sequestration. So overall, they concluded that AMP grazing mimics natural grazing patterns, improving soil health and vegetation diversity, and it also supports higher livestock densities as well, along with providing ecological and economic benefits. The study suggests that AMP grazing can be a sustainable practice for ranchers and can improve soil health and ranch productivity in the southeastern U.S. So now we're going to change gears a little bit and go from a setting where we're a controlled setting, like in a ranch land, and we're going to look at some property, or look at a study where they're looking at more native environments that aren't managed. So this case study comes from Ravi et al., 2017, and they're looking at ecohydrological interactions within fairy circles in the Namib Desert. So we are all familiar with seeing vegetation patterns in field and even in our own lawns. These vegetation patterns are often a recurrent characteristic of water-limited environments and are considered indicators of abiotic processes like soil moisture, infiltration, and runoff. However, rapid changes in patterns are recognized as early indicators or warning signs of environmental change like desertification in dry lands. So what this means is a better understanding of the formation, structure, and growth of the vegetation patterns and their interactions with hydrologic factors can improve our current understanding of important processes underlying dynamics of water-limited ecosystems. One area where these vegetation patterns are common is the interior margin of the coastal Namib Desert. And this is from southern Angola to northern South Africa. And these patterns are often referred to as fairy circles, and you see that in the title, and they can be recognized as millions of circular patches within the arid grassland spanning over hundreds of kilometers of this area. The goal of this study from Ravi et al. Was to address the knowledge gaps around the formation of these patterns, looking at soil moisture, soil texture, and infiltration, or hydraulic conductivity across multiple fairy circles in the Namib Desert, ultimately hoping to better understand the implication of these findings on the self-organization hypothesis of the fairy circle formation. So when looking at this study, we're going to primarily focus on the findings from the infiltration measurements because there's quite a bit of work that they did, but we're going to primarily focus on the infiltration measurements findings from the study. Saturated hydraulic conductivity measurements were done using the SATURO dual head infiltrometer, and unsaturated hydraulic conductivity measurements were made using the mini disc infiltrometer. For the KSAT measurements, they were only able to measure inside and outside of the circles due to the measurement footprint of the device. You can imagine that the ring infiltrometer has a larger footprint, so it's harder to measure in some of the fine areas of those fairy circles. And you see those results presented in the lower right graph that you can see there. And then for the unsaturated hydraulic conductivity measurements, they were able to look at edge, inside and outside of the fairy circle rings because of the smaller footprint of the mini disc infiltrometer. And you see these results presented in the upper right graph. And what they found is that KSAT values within the circles averaged out to about 8.6 centimeters per hour and 4.32 centimeters per hour outside of the circles, or in the inner spaces between the circles. And what that shows is that the KSAT values inside of the circles were double the values of outside of the circle, which is a pretty significant difference. And these results, this relationship was also present in the unsaturated hydraulic conductivity values. And you can see that in the chart on the upper right. You see consistently the inside of the fairy circles had higher hydraulic conductivities than the outside, and the edge actually had lower hydraulic conductivity overall. And they kind of dive into that as they look at some of the texture and some of the other things that are impacting that. But yeah, so the saturated and unsaturated hydraulic conductivities were consistently higher inside the fairy circles compared to the inner spaces between the circles at multiple locations. So this relationship was consistent when looking at at multiple fairy circles across this area. So what this means is that these were the results they found, along with some of the other findings around the soil moisture and the particle size analysis and the biometric measurements that they did, support the hypothesis of the self-organization theory. And so ultimately what happens is competition for water resources may initiate the fairy circles. And this will lead to the bare central areas that you see within the fairy circles. And this figure highlights some of these scale-dependent biomass water feedback loops that they present in the paper. And what ultimately happens is more water infiltrates inside of the circles and will likely provide water to plants along the edges. And then the lower hydraulic conductivities within the inner spaces outside of the circles could also be due to the results of soil crusts, both physical and biological, which is a common characteristic of dryland ecosystems. All right, now we're going to jump over to our third case study. And this case study is not an area of research that I would have personally seeked out, mostly due to cicadas being high on the list of bugs that give me the ick just a little bit. But it is really fascinating to think about the impact that macroinvertebrates have on hydrology. It is well known that macroinvertebrates and other organisms can have a pretty significant impact on soil formation processes. This is well known within soil science. And when you think about it, the emergence of macroinvertebrates is an interesting interaction to understand, because these biopores go straight to the surface. And so what that means is they provide a conduit for rapid movement of water. And this is somewhat similar to the impact that earthworms have on soil hydraulic properties. We know that they can have a pretty significant impact on how water infiltrates and what hydraulic conductivity looks like in the field. So the question is, can unique events like the 17-year emergence of the Brood X Cicada, can this emergence, which results in rapid disturbance of the soil with their large burrows, have a significant impact on the surface hydrology of an area? And of course, again, this was an interesting research topic to me for two reasons. One, does the spacing at which they emerge every 17 years, and two, does the size of the emergence, where some areas can have as many as 1.4 million cicadas per acre emerge, that's a lot, impact the hydrology of an area? So again, the study from Ficklin et al., they hypothesized that areas with high cicada emergence will have a great influence on infiltration rates and overall surface hydrology than in the proximal areas with little or no emergence. So to assess the impact that this emergence has on surface hydrology, After peak emergence, Ficklin et al. Measured field-saturated hydraulic conductivity using the SATURO at disturbed urban sites within Bloomington, Indiana, and in undisturbed forested sites outside of that area. And within each area, they made co-located measurements in areas with no visible emergent sites to allow for a direct comparison of soils in the same landscape and of course, in the same settings. And just to clarify, their definition of disturbance is whether the soils are currently influenced by human activities and whether these activities remained similar since the last emergence in 2004. Along with the infiltration measurements, they also counted the number of burrows present within the infiltrometer ring to serve as a proxy for density of the emergence. And you can see some of those pictures in the lower left there. You can see the ring inserted into the ground and how they're counting those burrows. And you can just kind of see what their setup look like out in the field. So through their research, they found that the field-saturated hydraulic conductivity was greater in undisturbed soil that contained cicada burrows, with a median KFS of 14.1 centimeters per hour when compared with the undisturbed soils without burrows with a median KFS of 7.8 centimeters per hour. And you can see that in the chart in the graph on the very right, titled undisturbed, and you can see that difference in hydraulic conductivity. On the flip side, however, the disturbed or urban soils did not show a significant difference, with a median KFS of 4.2 centimeters per hour in locations with burrows versus 4.4 centimeters per hour in locations without burrows. So they actually saw lower median hydraulic conductivities in the sites with burrows than the sites without burrows. Now, if you look at the chart in the middle there, you can still see that they did see some higher hydraulic conductivities in some locations with the sites with burrows, but overall the median values were lower than the sites with no emergence or no burrows. Also, just wanted to highlight what their measurements typically look like in the chart on the very left. And that's just, you can see what the dual head method measurements look like and what a typical measurement would look like for something like this. So to dive deeper into the results, they speculate that this difference is likely due to the collapse of it, and this is in the urban and the disturbed sites. They speculate that the difference is likely due to the collapse of the underlying cicada burrow due to continued compaction from foot traffic and other activities after emergence. They state that the impact that the Brood X Cicada has on surface hydrology is likely temporary, but this temporary increase could impact the connection between the hydrological cycle and the forest nutrient cycles, as the increased infiltration carries soluble nutrients and other organic litter from the forest floor deeper into the soil profile, this is not something you would typically see in normal conditions. All right. Okay. So we're going to shift gears now and focus on our last case study. This case study comes from Ibrahimian et al., 2019. And this case study focuses on infiltration in urban green infrastructure. So now we're focusing on engineering applications, where the goal is to increase infiltration to help manage runoff in urban environments. Ultimately, that's where the title of this webinar was focused on. But of course, there are many applications where we're using hydraulic conductivity measurements. But I do find these engineering applications really interesting because we're trying to design systems to better perform and help us manage and infiltrate water faster and help us manage runoff. So urban green stormwater infrastructure, often referred to as GSI systems, like rain gardens and infiltration trenches, play a key role in mitigating stormwater runoff by promoting infiltration. The infiltration capacity of these systems, of course, is influenced by the soil's saturated hydraulic conductivity, and this is a critical component in GSI design and performance that we need to understand. However, KSAT varies significantly over time and across different locations within GSI systems due to factors like soil composition, compaction, biological activity, and measurement errors as well. And we'll talk a little more about that as we dive deeper into this. So in this paper, Ibrahimian et al. Hypothesized that spatial and temporal variations in KSAT can significantly affect the performance of GSI systems. They explore how automated testing methods for KSAT could improve measurement accuracy, and efficiency, and investigate how factors like biological activity and sediment deposition impact infiltration sustainability. So let's dive a little deeper into their approach. So during the study, the authors conducted a critical review of field and laboratory methods used to measure KSAT in GSI systems. They compared various in situ methods like the traditional double ring infiltrometer. They also looked at the modified Philip Dunn and the SATURO dual head infiltrometer. And they also examined factors causing spatial and temporal variations in KSAT, including vegetation, compaction, sediment characteristics, water quality, and seasonal temperature changes. And so these are all some of the things that we hit on earlier. I won't focus on all of these factors as I go through this presentation just because of time, but I highly recommend that reading this paper. I really enjoyed reading it. I thought it provided a really good review of all these factors that influence how the infiltration of water into soil. So I highly recommend taking a look at this paper. So let's dive into what they found and their results. So maybe it's not that unexpected, but they found that spatial variability of saturated hydraulic conductivity, or KSAT, in GSI systems is significant. Of course, this is what we see in natural systems as well, with KSAT values varying widely even within close proximity at a single site. So this meant that a large number of measurements are required to obtain a spatially representative KSAT. So let's just dive into an example. So in one of an example they give is measurements taken from various GSI systems showed coefficients of variation ranging from 57% to 178%. So really wide ranges of coefficients of variation, telling us that there's really a lot of variability in hydraulic conductivity across the site. Again, we see this in natural systems as well. This emphasizes the need for multiple measurements at different locations within GSI systems to accurately characterize their infiltration capacity. They also concluded that the geometric mean of KSAT values should be used for design purposes because it provided a more conservative estimate compared to the arithmetic mean. And that's something I would agree with. I typically, when looking at these measurements, like to use the geometric mean over the arithmetic mean because it is more conservative and because of the way these measurements are distributed, it's a better value to use. They also found that at least 10 measurements at each swale were needed to reduce the uncertainty of the geometric mean values. And they also proposed that 20 measurements would be ideal, but it also is not always feasible for people to make that many measurements. Also, when looking at the seasonal variability, they found that seasonal temperature changes significantly affect the hydraulic performance of GSI systems. Lower infiltration rates are generally observed during colder months due to factors such as increased water viscosity and potential freezing of soil pores. Especially this makes sense in that northeastern environment. The freeze-thaw cycle also plays a role in the seasonal variability as it can either improve or decrease infiltration rates by affecting soil structure. Despite the variability in KSAT, they conclude that despite the variability in KSAT, infiltration-based GSI systems are effective and reliable for long-term stormwater management when designed with consideration of temporal and spatial variations. And they also conclude that by recommending incorporating these variations into GSI designs and optimizing the number of field measurements for better accuracy. And of course, proper GSI maintenance and monitoring are crucial for sustaining performance over time. So those are all the case studies I wanted to go over. But before we close out, I just wanted to highlight, again, kind of hit on the importance of hydraulic conductivity and what it plays in research. And so I did a little search myself just to see how often hydraulic conductivity was referenced as a measurement in publications since 2020. And since 2020, there have been 9,350 articles referencing soil hydraulic conductivity measurements, which actually was a little surprising to me. I thought that was quite a bit. So it was really cool to see that. But also in that search, I found this really cool article and this paper from S. Gupta et al., where they actually put together a global database of soil hydraulic conductivity measurements for geoscience applications. And you can see some of the tables and data that they've collected for that database in the charts on the right there. I have the reference below. I highly recommend checking that out as well. It was really fascinating to see how people are utilizing and pulling together hydraulic conductivity data for their various research applications. So it's really fun to work on this and go through these case studies and see what people are doing. And with that, I will close for questions.
All right. Thanks, Leo. So yeah, we'd like to use the next 10 minutes or so to take some questions from the audience. Thank you to everybody who's already sent in your questions. There's still plenty of time to submit your questions, so please feel free to add as many as you'd like. We'll try to get to as many as we can before we finish today. If we don't get to your question here live, we do have them recorded, and somebody, including Leo, will be able to get back to you, one of our meter experts, and they will respond directly to your question via the email that you registered with. All right. That being said, let's go to our first question here. You just quickly mentioned some issues with seasonality and taking measurements seasonally. Could you address seasonal variations and how you can deal with taking hydraulic conductivity measurements in different seasons? Yeah.
So that's something that I think is fairly well established in literature, is that hydraulic conductivity is both spatially and temporally variable. So what that means is and this depends on different sites. I think there's some locations where the temporal variation is less, but you have things that like antecedent soil moisture that impact hydraulic conductivity. You have things like temperature that impact hydraulic conductivity. And so what I suggest doing, there's a couple of approaches you could take. One, for temperature, if you're not dealing with freezing conditions, you can normalize for temperature to a set point to help kind of allow your measurements to be more applicable across time. But ultimately, in many cases, what you have to do is you need to take measurement across those seasons to really understand what's happening, especially when you're dealing with expansive soils and soils that might have freezing of pores and things like that, because we can't really model that out. And so really what you have to do is you have to take the measurements to really quantify what's happening. But it's really important that when you're taking these measurements that you also collect ancillary data like the antecedent soil moisture, what was the soil temperature, what's your water temperature. All of those things really are important to help better understand what your measurement means across everything, and also to help understand what factors are actually the things that are impacting the changes in hydraulic conductivity.
All right. We actually have a couple questions in here asking about remote sensing. Is there any potential, or what's going on in the realm of remote sensing when it comes to hydraulic conductivity?
Yeah. Wow. Okay. That is a really good question. And unfortunately, I'm not much of an expert in remote sensing. I mean, I know a little bit in that area. I'm not super familiar with people using remotely sensed data to quantify hydraulic conductivity. I think what is interesting is you can use remotely sensed data to identify areas of variability. because you can look at things and see where you may be seeing variability due to soil moisture or vegetation or things like that to help you decide where you need to make measurements to quantify where there might be differences. And of course, identifying, the different seasonal differences that you might see. But I'm not familiar with any methods, remotely sensed methods for quantifying hydraulic conductivity. And if you do know any, I would love to learn more about them.
Let's see. This individual is asking if it's feasible to consider a permanent measurement system just to monitor hydraulic conductivity, say, for instance, in an urban setting.
Yeah, that's a really good question. I think it's really hard to have a permanent system specifically for measuring hydraulic conductivity, but an approach you could take, which is also not, I don't think is a bad approach, is to have sensors installed to measure soil moisture and water potential, because if you can track your changes in soil moisture and water potential and you have known intervals, so known depths that you're monitoring these, then you can actually look at those wetting fronts, how fast they're moving through soil, and you can use the water potential and water content data to try and assess your unsaturated hydraulic conductivity to some extent. It's not perfect because there's sometimes lag in some of the measurements and some of those things, but we've played around with this ourselves where we actually try to use our field data to quantify unsaturated hydraulic conductivity. But when it comes to saturated hydraulic conductivity, that would be really challenging to have a permanently deployed system. But I'm always open to new ideas.
That actually hit my next question, which was they were asking about using soil moisture sensors at different depths as a proxy for hydraulic conductivity. So good job hitting that. Let's see. This next one, they're asking, what happens to the measurement if the soil is in a saturated soil condition versus unsaturated?
Okay, that's somewhat not a fully loaded question, but if you're making hydraulic, and I'm not sure if this is referring to the field measurements like with sensors installed or the measurements with a device to measure hydraulic conductivity, but typically what happens if your site is actually completely saturated, you're actually going to see no movement of water into the soil because at some point it does stall out. But of course, when you're making these measurements and when we're making hydraulic conductivity measurements, and you saw one of those examples, actually, I'll just go back to it really quick. You can see what happens as we're infiltrating water in the unsaturated conditions. Initially, the infiltration rate is higher, and then as the soil becomes in our measurement area becomes saturated, you see that measurement plateaus or reaches what we call a quasi-steady state, and ultimately that steady state value is what we're using to get our hydraulic conductivity value. Hopefully that somewhat addresses that question, but there's a lot of things that impact how water flows into soil within the whole system.
Okay. This might get a bit too much. We might need a bit more time for this one. They're just asking a comparison between the SATURO's dual head method and, say, for instance, the drill hole method or other ways to measure hydraulic conductivity. Yeah.
So that's a really good question, and is maybe leading for me because that's an area that we're working on. But there are differences, and this is well known that one, when you're infiltrating from the surface with something like the SATURO, you're measuring the water as it's moving through the whole profile. So that whole profile, as the wetting front moves through, depending on how deep that wetting front moves through, it's that profile that's controlling it. The borehole methods are awesome because now we can dive down into deeper layers and understand how deeper layers are impacting long-term movement of water into soil. And so they are both important measurements to understand. This is something that we've been messing around with. And so I think, they don't, depending on how you set up, they don't compare well because typically when you go into a borehole, you're not looking at the surface, you're looking at deeper layers. And so it just depends on the soil profile and how it's made up, and those measurements might not always compare well.
All right, we're running up to the end of our time, so this is going to be the last question. Again, thank you for all the great questions. There's a few that we didn't get to. We will be able to get to those via email. All right, last question here. Similar to what you were talking about, they were trying to get at deeper at deeper depths. They're trying to get deeper hydraulic conductivity measurements. They were wondering about being able to do lab measurements. So being able to take samples back to the lab. They're mentioning using KSAT, HYPROP, if they can be able to gauge hydraulic conductivity. Again, it's going to be disturbed sediments, not in situ. Can you go into detail a little bit about that process?
Yeah. So this is actually a topic that I've hit on in the past as well. In some of our past webinars, we talk about the differences between lab and field methods. You can do that, and you can take cores too at deeper depths. That way you have at least an intact sample to take back to the lab. And the challenge, of course, is in the lab with that. Now, what I love about the lab methods is we can isolate specific areas that we're trying to measure and understand these individual layers and what they're contributing. The challenge is in the field, we're looking at the whole interaction of those layers, whereas in the lab, we're looking at isolated portions of the soil. And you also sometimes see differences because you can take a core from the field and bring it back to the lab, and that core might have a pore that's open-ended that typically wouldn't be open-ended in the field. And so you could see differences due to that. But then, of course, there's a lot of factors that can impact how lab and field measurements compare. But I'm not going to say one is better than the other because I think they're both super important. It's just you need to understand the limitation of what you're looking at. So with the lab measurements, it's typically isolated. We're looking at specific layers. And in the field, we're looking at more so whole interactions within the whole profile and across the field.
All right. Okay. That's going to wrap it up for us today. Thank you again, everybody, for attending and participating in this discussion. We hope that you enjoyed it as much as we did on our end. Thank you again for all your great questions as well. Please consider answering the short survey that will appear after the webinar is finished, just to let us know what kinds of webinars you'd like to see in the future. And for more information on what you've seen today, please visit us at metergroup.com. Finally, look for the recording of today's presentation in your email and stay tuned for future Meter webinars. Thanks again, stay safe, and have a great day.